Okay, good afternoon. Welcome to the 46th ASE seminar, Advanced Supercomputing Environment. And so before starting the seminar, I'd like to briefly overview the history of this seminar. So this seminar was started 16 years ago, March 2008, by Professor Takahiro Katagiri. He's now in the Nagoya University. And so this is an irregularly held meeting. When we have a domestic and international visitors to the Information Technology Center, we have this seminar. Okay? And the topic is not limited, but so related to HPC and supercomputing. And the last meeting before COVID-19 was the 40th on February 4th, 2020, okay? 4 years ago. And the online 41st meeting on February 4th in 2022. And the first hybrid seminar was the 42nd on April 11th last year. And this is a fifth hybrid seminar. And so I'm happy to welcome the visitors to this center. Okay, so the subtitle is Japan-France international collaboration in the integration of simulation data learning and the Fugaku-Next supercomputer system. So this title is a little bit misleading. Okay, so we have two parts. First part is a Japan-France international collaboration in the integration of simulation data learning, and the Fugaku-Next supercomputer system is it's a separate topic. It's not a direct collaboration between Japan and France. I believe every research related to HPC between France and Japan will lead to the Fugaku-Next supercomputer system, but today it's a separate one. So we have two excellent guest speakers from France, Professor Serge Petiton from University of Lille and CNRS, and also Professor Nahid Ahmad from University of Paris-Saclay Versailles and Maison de Simulations and L.I. Palat. And Serge Petiton is his third appearance in this seminar. And I just checked the past program, and the last appearance was October 23rd, 2013. It's more than 10 years ago. So this is a program. So we have 6 talks with some break. Okay, so I'll start my talk. The title is the integration of simulation data learning and beyond. And also I'll talk about the Japan-France international collaborations. My name is Kengo Nakajima. I'm a faculty member of the University of Tokyo Supercomputing Center. So I'd like to acknowledge my sponsors. And so this is the very brief overview of my talk. We start from some hardware and software related to the integration of the simulation data and learning, and some applications, and also some future issues. And I'll talk about the collaborations with the French institutes and summarize my talk. So this is a history of our system in our supercomputer center of the University of Tokyo. So we have nearly 3,000 users, but so more than 55% of the users are outside from the University of Tokyo. And you can see we have more systems with green tags, which shows the GPU and accelerators. So this is a research area based on the machine hours in the 2022. And we have 2 CPU systems and 1 GPU system. And you can see we have a very different workload. So in the case of the CPU, traditional CSE, computational science and engineering, such as engineering, earth and space science, material science, and energy and physics are so dominant. But in the case of the GPU cluster, we still have a big users for the CSE, but we have more users for the AI and bioinformatics. Now, the supercomputing is changing. As I mentioned, we have various types of workloads. So in addition to the very traditional computer science and engineering, we have a new research area and also new users, such as the big data analytics, AI, and machine learning. And we thought that the integration of the simulation data learning, we call this S plus T plus L. So this is very important towards the Society 5.0. It's a human-centered society proposed by Japanese government by integration of cyberspace and physical space. And we call this paradigm as a BDEC, so big data and extreme computing. And it's a platform for integration of the S plus D plus L. But in our case, we are focusing on S, so simulation. So simulation is a big part. And the data and learning are supporting simulations. So this idea is called AI for HPC or AI for science. We started this type of the approach from 2015, so nearly 9 or 10 years ago. So we still be the one, which started its operation May 14th, 2021, 3 years ago. So this is our first BDEC system, and it's a platform for integration of S plus D plus L. The total peak performance is 33 petaflops, and the aggregated memory bandwidth is 8.38 petabyte per second. It's by Fujitsu. Okay? So we have two types of the node groups. One is the simulation node group called Odyssey. So it's based on the Fujitsu's Prime HPC FX1000. It's a commercial version of the Fugaku supercomputer. And the total peak performance is nearly 26 petaflops. So another part is the data and learning node group, Aquarius, for the data analytics and AI machine learning. And it consists of the Intel Xeon Ice Lake and NVIDIA A100 GPUs. And totally, we have 360 A100 GPUs, and the peak performance is 7.2 petaflops. And some of this part connected to external resources, such as sensor networks directly. Okay? So this is how we utilize these systems. And so you can see, so we need a lot of parameter studies for real world nonlinear simulations. Okay? But so by supported by the data assimilation and machine learning, we can optimize the models and the parameters, and we can accelerate these cycles for the parameter studies. So this is how we utilize this system. So again, so this is a research area based on the machine hours last fiscal year, and this year, so it's almost same. But you can see, so in the case of this GPU part, we have a very different colors compared to other part. So this year we have a big experiment for the large language model. So therefore, so more than 25% of the usage for this GPU part is spent for AI and machine learning. And also this bioinformatics area is increasing part, and it's related to genomic analytics or medical image recognition by machine learning. So it's a new area of research and users. So this is a hardware, and we are also developing a software. So it's an innovative software platform for integration of S and D and L on the BDEC system. So it's called H3 Open BDEC. So it's a 5-year project supported by Japanese government, JSPS, since 2019. So actually, so this is the last fiscal year. So this is in the end of this March. Okay, leading PI is myself, and total budget is $1.4 million US. So this is our core PIs, so which covers a wide range of the expertise: computer science, computational science, numerical algorithms, data science, and machine learning. And this is a list of the contributors and collaborators. And also, we have many international collaborators. Okay, so this is a part of the list that you can find here. Okay, so we have 3 innovations. First one is utilizing the lower precisions and accuracy verification. This is a numerical algorithm part. And so details of this part will be given by Dr. Kawai in the 4th talk of today, and I skip the details. And the second one is the integration of the S plus D plus L, but I also skip this details of this part. And the third part is the software and utilities for heterogeneous environments, such as Iterative, so I focus on this part. Okay, so Iterative is the first really heterogeneous system in the world. So we have many centers which are operating several kinds of the systems. But this is the first system, so it's really connected and working together. Okay. And you can see, so we have two parts, Aquarius based on the NVIDIA GPUs, and Odyssey is based on the ARM CPU. And combining these two parts is very difficult. So single MPI job over Odyssey and Aquarius is impossible. Okay? But connection between Odyssey and Aquarius is so by this InfiniBand EDR network. It's a very rich network where the network bandwidth is 2 terabytes per sec. And also we are connected to the first 5 systems. And we developed a system software, H3 OpenSys Wait IO socket. Usually we call this Wait IO. It's a library for inter-process communication through InfiniBand EDR with MPI-like interface. So you can call this Wait IO library by this type of the interface. It's very similar to MPI and from C, C++, and Fortran language that we can easily combine these two parts. So another important tool is a multi-physics coupler. A traditional coupler, so which we developed in the previous project, it's a weak coupling of multiple applications, usually 2 applications. So each application does a single computation, like ocean, atmosphere, and fluid and structure. So actually, so our former coupler, PP-MP, was a ocean and atmosphere coupler, and we did some simulation for the super El Nino on K-computer. Okay, so this is a very nice result. But this time, we try to extend this idea to the combination of the simulation and machine learning or AI workload. So in this case, we are running the simulation workload on Odyssey and machine learning AI workload on Aquarius. Initially, our coupler was for this type of the homogeneous systems using MPI. But June 2022, almost 2 years ago, we integrate our coupler with the Wait IO library. Then we can run the combined work on the heterogeneous systems. So thus, users of our Wisteria VDX01 system can enjoy the heterogeneous computing. Okay, so I'll show you some examples and applications. So first one is a 3D earthquake simulation with a real-time data observation and assimilations. We have a very big earthquakes in Japan in the New Year Day. And so the idea of this simulation is combine the real-time data observation by this type of the network with some seismic wave propagation. So in Japan, we have a real-time sharing of the seismic observation by the JDXnet. So it's operated by some governmental organizations and universities in Japan. So we have more than 1,000 observation times, and so it's 100 hertz. So every second we have 100 times observation, and we can get the data through SciNet, so which is a Japanese academic network in real time. The size of the data is roughly 400 or 500 gigabytes per day. And so this data is available at the website of the NIED. So Natural Institute or some natural disease environment institute in Japan. So traditional idea for this type of wave propagation is that we assume some source terms here at the epicenter and so do the computations. But it's very difficult to define the proper and accurate source term. And if you apply the wrong source terms, we have a very wrong answers. So instead of that, we try to utilize the observed data. So these yellow triangles mean the observational point, and we just interpolate the observational result and correct the solution by this way. So in that case, we don't need this source term. So we start from the combination of the data assimilation and simulation. Then switch to the pure simulation at certain time. Okay, so this is a formula for the data simulation. It's a very simple. Okay? It's just an interpolation of the observation point. So this is a system which we constructed on the Iterative VDEX. So we can get the JDXNet observational data, and also for the big earthquakes, we can save that on the external server. And we can introduce these observed data to the Aquarius, and we apply the filtering for the precondition. Then we send the data to this Odyssey part, and we are doing the computations and simulation by Seism 3D Open SWPC DAF. So this is the name of the code. Then we go back to the Aquarius for the visualization. So this is a code. It's a Fortran code, which is describing the sending the filtered data from Aquarius to the Odyssey. And this is the Fortran code. And you can see we are calling call wait IO MPI I send for this side. Okay, so many times. And at this part, we are calling call wait IO MPI I receive. So that's we can do the communication between these two parts easily. Okay, so this is some simulation result. So another application is a global cloud simulations. Okay, so generally speaking, so we do this type of the simulation combining very detailed model and with a very coarse model. Okay, so this coarse model is for the some defining the parameters, and this process is called parameterization. And generally, so 75% is spent for this detailed model, and 25% for this coarse model. So our idea is replace this parameterization part with AI. Okay? And this is on Odyssey, and this is on Aquarius. And inference part is very small, so we can reduce the time to 0. Okay, then we can accelerate the computations. Okay, so in this preliminary study, we are choosing the density and internal energy and density of the vapor as a parameter. And we estimate the gradient in time direction of these three parameters. Okay, and I skip the details, but we are using a very simple 3-layer perceptron. Okay. So this is the result. So this is the input, and this part is real simulations. And this one is a prediction by machine learning by neural network. And you can see they are very similar, but we have several problems for capturing the peak. So we are now improving this part by introducing some more parameters, and it's getting better. And also we are doing some collaboration with Sambanova, and we try to substitute this part or this part with the Sambanova AI chips. Okay, so if you run this type of the workload, so actually we have two types of the computer nodes. And the Odyssey has nearly 8,000 nodes, and it's not so crowded. But Aquarius has only 45 nodes and very crowded. And one node of Aquarius is reserved for this type of workload on the integration of S plus D plus L, and two separate jobs should be submitted. And if both job grabs resources, execution starts. So this is not so flexible, and we are seeking more flexible. And also it's more complicated policy. Okay. So last one is the ensemble coupling. Okay. So first, I'd like to show you the ensemble-based data assimilation. It's a very popular method for the weather and the climate simulations. And it combines data assimilation and ensemble simulations for accurate predictions. So in this case, so we have 9 cases, and generally, so we have 64 or 100 cases for weather prediction. But it requires significant computer resources for high-resolution simulations. For example, if you simulate the 9-hour simulations using the 64 cases, if you utilize the 320 nodes for each part, and we need 7 hours. And it's so leads to the more than 2,000 node hours. Okay, so this is a very expensive. So idea of the ensemble coupling is a coupling low resolution ensemble data simulation with a high resolution simulation. So in this case, we are just running the one case of the fine mesh and 64 cases for coarse mesh. So in this case, we have a 40 kilometer resolution, 14 kilometer resolution for the fine simulation, and the 224 kilometer ensemble data. So it's a very different. Okay? And we are doing the preliminary result and replacing the this higher resolution part with this lower precision, lower resolution, and also we apply the single precision instead of the double precision. And finally, the result in the performance are improved over 100 times. Okay, so original more than 2,000 times is less than 20 node hours now. Okay, so this is our preliminary result. And so in this way, we can get a very nice performance improvement in the area of the weather and climate simulations. Okay, so I'll talk about next phase. And basically, so this weight IO library, so this is developed by my colleague, Professor Sumimoto. So it's a very flexible and useful library. And we can connect any kind of the architectures from CPU to GPU. Okay, so I'll talk about our next system, OFP2. Okay, so it's just so bit was opened last year, at the end of last year, and Fujitsu awarded. Okay, so this is a joint work with the University of Tsukuba, and so we are shifting to the GPU cluster. Okay, we still have a CPU only part based on the Intel Xeon Max. It's a Sapphire Rapid with high bandwidth memory. But it's a very small portion. And the big part is this GPU cluster. It's based on the NVIDIA GH200. It's a so-called Grace Hopper super chip. It's an ARM architecture and NVIDIA H100 GPU. Okay. So we have totally over 1,000 nodes, and the peak performance is 78.2 petaflops was this part, combining the CPU and GPU. Okay, so all nodes are connected with a full bisection bandwidth, but so it's separately operated. But so we can connect these two parts with a weight IO library if we need. So if we want to do some kind of the workload utilizing both of the node groups, we can utilize that software. And we can also extend this idea to other parts, such as the quantum computers or AI chips. And we are now starting the new project for QC, quantum HPC hybrid platform from this year. So it's a 5-year project. And the name of the project is JHPC Quantum. Okay? So main contractors of this work is RIKEN RCCS and SoftBank. And the leading PI is Sato-san. Okay? And University of Tokyo and Osaka universities are cooperating organizations. So it's supported by this governmental funding agency. And in this project, we are installing the 2 real quantum computers. One is the IBM's over 100 qubit systems, and another one is the ion trap system. So it's a smaller one, but it's more stable. And our idea is quantum computer as an accelerator of the supercomputers, such as GPU. So this is the idea of the QC-HPC hybrid. And the role of the University of Tokyo is the research and development on the system software for QC-HPC hybrid environment. Yes, we have many sub-projects and we are doing this part. And in Japan, quantum computers and supercomputers are not necessarily located in the same location. So therefore, special meta scheduler or cost scheduler, which coordinates the multiple systems in the remote locations, is very important. And we also need the remote communication library and tools among such systems like this. And we are developing a system software for the efficient and smooth operations of the QC-HPC hybrid environment. One is a QH scheduler, so it's a job scheduler, so that can combine these systems. And also, we are developing the H3 Open BDEC QH. So it's an extension of the H3 Open BDEC in the previous part. So target applications are quantum simulations and error correction, error mitigations. And personally, I'm very interested in the quantum machine learning and combined with the simulations. Okay? So we have several quantum computers, including simulators, and so several supercomputers. So this is the world's first attempt to link multiple supercomputers and quantum computers installed at a different site in real time. In particular, by using multiple quantum computers simultaneously, so it is possible to form a virtual quantum computer with higher processing capacity, so qubit value. I thought that this is a very good idea, but last year I attended the ASE 23, and many people are thinking about the same thing all over the world. So, but this is the right way. Okay, so I'll talk about some collaboration with a French institute. So I just briefly overview the history of the collaborations between our center and the French institute. And the initial one is the FP3C. It's a framework and programming and post-petascale computing. It's a JST-ANR collaboration between 2010 to 2013. It's 10 years ago. And the PIs from the French side was Professor Petiton, today's speaker, and Professor Sato, he's now in RIKEN. From Japan, 4 universities joined, and several institutes from France. And also, we have ADAC activities. So this is an overview of the FP3T, and I believe this is a very nice opportunities for starting our collaboration. And ADAC, Accelerated Data Analytics and Computing Institute. So it started as a consortium of the GPU computing, but it now provides a venue for the international discussion on future of the supercomputing and supercomputers. And we have 16 members, including USA, Japan, Australia, and Europe. And University of Tokyo and CA are the members. And so every year we have 2 or 3 workshops. And last workshop, last September, was in Paris. And this was a very nice meeting. And also we have some collaboration for the JHPCN project. It's an innovative computational science by integration of the simulation data and learning on the heterogeneous supercomputers. It started this fiscal year. And also we have a CEA RIKEN collaborative research. We started that 2017, but it's some overlaps with the JHPCN project because some of us are collaborating with RIKEN, and we are also participating in this collaboration. So I skipped the detail of the JHPCN. So it's some framework for providing the supercomputer resources. It's a proposal-based, and we are hiring the international project. So our project started this fiscal year, and I'm planning the 3 years. Okay? So it's a Japanese institute, and also German and French institute, and Croatian institute. And so nationality of the participating researchers covers 12 countries. Okay? 2021 and 2022, we focused on the earthquake simulation. But from 2023, we include the other applications and also started the international collaborations. Main purpose was the popularization of the software usage, which we developed in the H3P OpenVDEC, such as Wait.io or Kepler. Okay, we have several target systems for the Zurich Supercomputing Center and CEA from France. And I just skipped the details of the purpose and background. And that in 2023, we have mainly focused on the porting our international partners' code to our system. But next fiscal year, so we try to extend the idea to combining on our supercomputers. Okay, so this is one of the examples. So it's an earthquake simulation by PSD. PSD stands for the Parallel Seismic Dynamics. And this was developed by CEA. Okay? And as I mentioned, we are focusing on the earthquake simulation using our code. And our idea is trying to introduce the data assimilation capability to this PSD code. And also, we explore the machine learning-based earthquake propagation prediction through causality. Okay, so causality. Okay, so aiming to improve simulation efficiency or deepen data understanding. Okay, so this is our new approach. So another one is a big DFT is so Genesis for SARS-CoV-2. So this is the name of the virus for COVID-19. And we try to do this kind of simulations, combining quantum mechanics and molecular dynamics. And the molecular dynamics part is by Genesis, developed by the RIKEN, and the quantum computer part, quantum mechanics part is by Big DFT. It's an open source code, but it was already optimized for ASE for FX under CEA RIKEN collaborations. And we run BigDFT, Odyssey, and Genesis on Aquarius, and so try to couple by our software. Okay. So we are also co-organize a series of the mini symposiums in Science PP and CESE conference since 2010. So nearly 15 years. And then, so this year in March, we have a Science PP 24 in Baltimore. So we have another co-organized workshop. So last one is a Hanami project. So it's starting next month. Okay. So it's a real name is the HPC Alliance for Applications for Supercomputing Innovations. It's a EU-Japan collaboration supported by Euro HPC JU. Okay. So it's a 3-year project focusing on climate, weather, life science, and material science. And the main EU HPC centers, such as CEA, JSC, or Barcelona Supercomputing Center, are participating. Unfortunately, Japanese side is not funded, but HPCI centers will be involved in training and human resource development and utilization of the mutual HPC resources. And so JHPC project, which I mentioned, is also involved in this Hanami project. So we have many past and ongoing and future collaboration between France and Japan. Okay, so thank you very much for your attention. Okay, so next speaker is Professor Nahid Ahmad. And the title is Unite, Learn, Iterative Approach for AI.
So thank you. This presentation is about using numerical algorithm, numerical algebra, high performance numerical algebra in machine learning. So I would like to say that in a large model, in every step of the large model, we have the appearance of linear algebra problem. For example, if we consider transformer, we can see that if we consider just the embedding layer of the transformer, we can see that we have many of linear algebra problem. For example, the building of covariance or co-occurrence matrices, also sparse computation, and a very important part of these layers of the reduction of dimension. And the reduction of dimension is the topic that I focus in this talk. You know, in linear, the interaction between linear algebra and machine learning, it's, I can say that is evident because in many steps of machine learning, we have the linear system of equation and linear transformation. Linear transformation, it's the part that I focus on is about the eigenvalue computation. And eigenvalue computation, it's a very important part of linear algebra. And this part is evidently used, I would like to say, eigenproblem is used on many methods, many techniques in machine learning, such as principal component analysis, or all derivatives of PCA. So it consists of computing of dominant eigenvectors of the matrix representing data set, and for computing the dominant eigenvector of this kind of data set, we have to know that the associated matrices is very sparse and is very, very large. This corresponds to the reduction of the dimension of data set, the matrix representing data set. So as we speak about very large eigenproblem, that means we have to be able to exploit efficiently the high scale architectures. We have to use adaptive programming paradigms, perhaps to define new methods, and all of these for the objective of to do big data analytics, high performance big data analytics. For that, my talk is in 4 points. In the first, after defining some interaction between linear algebra and machine learning, I will introduce unite and conquer method in high performance linear algebra, and we will see after how we can apply this concept to machine learning, some machine learning topics, problems. So a very rapid look at machine learning methods, we can see the appearance of eigenvalue problem, linear system, and SVD, and all kind of linear algebra problem in machine learning techniques. As I focus on eigenproblem, I would like to highlight the fact that eigenvector is a very important concept. That means concept of data set. That means that an eigenvector, contrary to the case of any vector, the multiplication of eigenvector by the corresponding matrix doesn't change the orientation of this vector. And this is very important, that shows, it shows that eigenvectors are very robust as vector containing the information of the matrix of the corresponding data set. So, for this reason, we can consider eigenvectors as the backbones of data set. This is the reason that when we compute the dominant eigenvectors of a matrix representing a data set, these dominant eigenvectors are considered as the principal axis of data set, and they contain the most important information about data set. And I insist to say that the computing the dominant eigenvectors corresponds also to the reduction of the size of data set. So the key element now is that we have to use, as we have a very large sparse data set, we have to use iterative method. This is because of Abel theorem that we can't compute the eigenelements of a matrix, a very large matrix, by a direct method. So for solving this kind of large and sparse linear algebra, especially eigen problem, we use iterative methods, but iterative projection or reduction method that allows two important properties, preserving sparsity, and the second important property is the reduction of the dimension, because we don't compute all of the eigenvectors, but just the dominant eigenvector. That means we suppose that our problem is defined in a very large space. So we define an initial subspace. We do the reduction or projection on this initial subspace. We compute some approximate solution. And if these approximate solutions are not sufficiently accurate, so we begin, we restart the process with a new subspace. That means we restart the projection, but with a better subspace. For defining this subspace, this better subspace, we make use of the solution obtained in the previous iteration. So two problem of this kind of method is can be solved, because with this kind of method, iterative method, we have to we have a sparsity of the matrix that preserve it, and also we have a Kirillov subspace if we decide to use a Kirillov subspace at subspace of projection. Now, I would like to say that when we have a Kirillov subspace, we have two parameters: the initial vector and the size of the subspace. The initial vector is what we use to improve over the iteration. During the iteration, for each iteration, improve the initial vector of the previous iteration. So the process consists of this one. Here, I would like to give just one example of this kind of method. That means the restarted, implicitly restarted Arnoldi method, and that is the general structure of this kind of method. That means we do the reduction of the dimension here. If the dimension of the initial problem is n, with m, which is very smaller than n, we can do the projection in the subspace with m size, and we solve the problem in the subspace, and we will have some approximate solution in C step. And if we have convergence, we stop. Otherwise, we do some restarting strategy to re-begin the process from A step. But I would like to insist to say that here we only consider V initial vector, and we improve over the iterations this initial vector, this restarted vector. But the question is, what about M? Why M is also, M is the size of the subspace, but we don't use M as a parameter also. So this question is the subject of the next part of my talk for unite and conquer approach. You know, unite and conquer approach consists of, by opposition to divide and conquer, which we divide the problem on sub-problem, and we combine the solution of the sub-problems to give a solution for the initial problem. Here we have a problem, and we have several methods that we call co-methods, and we make collaborate all of these methods to solve the same problem. The collaboration consists of communicating the intermediary result of each of the co-methods. And as you see here, we have many interesting properties of this kind of method in viewpoint of computation. And that is very good because we can have, if we have chosen a good strategy for restarting these methods, we can have very good result performance, accuracy of the results, and time to solution. This is, we have done many works with many colleagues and the students on this kind of methods, unite and conquer, and this reference is about the synthesis of all of these works. So anyway, I would like to speak about a particular case of unite and conquer, which we call multiple method. And in this case, we have exactly the same method to solve our problem, but we do the initialization of this method differently. That means we use several instances of the same method, and we make collaborate these co-methods in order to have good property of convergence. So we defined many unite and conquer methods, multiple methods such as multiple RAM, multiple ERAM, and some cases of this kind of method, which is with the nested subspaces, etc. So we consider here, we can see that if we have, if we want to compute K dominant eigenvector, we can choose in the case of nested subspaces, these subspace sizes, which are very, very smaller than the size of the data set, initial data set. So I would like here to give the example of multiple implicitly restarted Arnoldi method, which is defined that in the first we can see implicitly restarted Arnoldi method. You know, we have exactly the same part of projection, the reduction of the matrix, initial matrix, solving the problem in the subspace, and computing some approximated solution, the K approximated solution if we haven't convergence. So we continue. The process of implicitly restarted consists of considering some treatment of the problem in the subspace. This treatment consists of to do the discrimination between the wanted information and not desired information. And when we do this separation between wanted and unwanted information, we can reject the unwanted information and give the part of the equation that is that corresponds to wanted information. This is all of this equation with only k parameter. So we reject the rest of it and we re-begin to complete the Arnoldi projection, to define a new Arnoldi projection up to the subspace size M. So unite and conquer in this case consists of doing several projections, several reduction in nested subspaces, as here. We compute the approximated solution. We choose the best of this approximated solution, and we do the treatment by QR shifted algorithm on only this subspace, the subspace corresponding to this best subspace. And we can have very good results that is not explained in detail here, but the result is very interesting because we can have the solution of the problem, of the difficult problem that we haven't otherwise. For example, here we can see the performance, the convergence by multiple implicitly restarted Arnoldi method here in red, but with implicitly restarted Arnoldi method, which is very robust method, is not possible to have the convergence. You know, I would like to show in the same, in the left, we can see we have the convergence very rapidly with multiple implicitly, and it is not the case of implicitly restarted Arnoldi method, basic method. So what I want to say that we have the proof of convergence. It's very good. But another problem that I want to highlight here is that contrary to what we think mathematically, that the best subspace size is the largest one, it is absolutely not the case. And we can see that the best subspace here, we can see the best subspace size during the iteration, and the best one is very often the smallest one. Here is the same. We have the best one is the smallest one in general. And we can deduce here that this method can give us, by computing, by more computing, the best subspace size in each iteration, but this is a good example to make use of machine learning techniques and detect automatically this kind of parameters. So anyway, you know, this kind of method has many interests in point of view of convergence, but the asynchronous communication between method has the consequences to introduce non-determinism. But non-determinism, this problem doesn't exist in machine learning technique. And you know, if we apply this approach to machine learning technique, this problem doesn't appear. So in the last part, I would like to show the application of this approach, unite and conquer approach, to clustering and cyber security, and especially more generally anomaly detection. So the focus on clustering is that we can use K-mean algorithm and spectral computation by using also this new method, multiple implicitly restated analogy method. And we have the good result, as we are going to see by an example. And after we will see the problem of classification. So the problem here, the application of multiple implicitly Arnoldi method on the case of clustering consists of to see the problem of the detection of relevant groups based on frequent co-purchasing on Amazon.com. You know, the people that buy the books, political books oriented toward right, left, or in the center. And we want to separate, to discriminate this kind of books. For that, the machine learning techniques consist of two main machine learning techniques, are modularity maximization and minimum balanced cost. The first one is based on the computation of the dominant eigenvectors, and the second one, the eigenvectors of modularity matrix, and the second one is the smallest, based on the smallest eigenvectors of the Laplacian matrix of this data set. Anyway, if we use this method and its symmetrical version to solve this problem, and these methods are implemented and used in NVIDIA EnvidGraph library. So the algorithm is just these 5 or 6 steps. We can see that we have just the pre-processing of graph, defining the graph, defining the modularity matrix. After we have eigensolver to compute the dominant eigenvectors. Here we are forced to compute 3 dominant eigenvectors because we want to detect 3 groups. And after we make use of a machine learning technique for clustering, such as K-mean algorithm. So the profiling the modularity clustering can give us the importance of eigenvector, eigensolver in this algorithm. And we can see that the big part of the time, 90% of the time, it's passed on the eigensolver. And in the same manner, in the eigensolver, we have many time to pass for the sparse matrix vector computation. And the result is presented here. We can see the true case in the right and our clustering results here. And we have a good percent of accuracy, 84% of accuracy. The second example consists of classification for anomaly detection, and especially for cybersecurity case. But anomaly detection is very more general than cybersecurity. So the classification is binary classification and imbalanced classification. So the application of unite and conquer approach on this case, it's making use of ensemble learning and application of unite and conquer to this kind of machine learning techniques. Ensemble learning, 2 main parts of ensemble learning are bagging and boosting. Bagging consists of defining, dividing the database, the data set on bags, and working with some machine learning technique on these bags, and choosing the best one. And boosting is a kind of iterative process, but with a fixed number of iteration, because the number of iteration of the is the number of the methods, boosted method. So with the approach of unite and conquer, we do this kind of mixing, bagging and boosting, but with some robust strategy. And we have the number of iterations that is not fixed. And we have we have defined two framework. The first one is USIL for Unite and Conquer with ensemble learning. And this figure shows how we do this mixing. And we have the result of this framework is sufficiently interesting to be integrated in an alarm system for Evident company, the branch of cybersecurity of Evident company. And concerning the performances of this USIL framework, we can see that the accuracy of the results of USIL is here and is the best with respect of each of the co-method machine learning co-methods. And here we have the same co-method, but this is the instances, different instances of the same co-method. But here we have 4 different anomaly detection co-method, and we have in the same manner we have very good result concerning the accuracy of the algorithm. So here we see some computational performance as weak and strong scalability, but we can see that we have some problem here. This is because of the synchronous communication in this version of the algorithm. We haven't the result of the asynchronous communication not yet. So this is the second version of Unite and Conquer, applying Unite and Conquer to bagging and boosting. And this version is more robust and give very good results. This is in collaboration with Numerics, which is a company, cybersecurity company in France. And we have the result of this version is very impressive in the sense of the accuracy obtained by this framework is almost perfect. We have more than 99% of accuracy, and we can see that the difference between the accuracy of trained data set and test data set, it's very near. That means that even for this method, the data that it doesn't see never can be considered very well and with very well accuracy. Here also we can see scalability of this second framework with respect of the data size. So to conclude this talk, I would like to say that it's interesting to do some algorithm by ourselves, because we have the possibility to bring innovation in algorithm part of high performance linear algebra, such as the Unite and Conquer approach. Because when we use always the libraries, we don't give to ourselves this kind of possibility. We have to work more between linear algebra and machine learning. There is many good opportunities to take advantage of linear, high-performance linear algebra in machine learning and vice versa. And also, there is really a tsunami of solution from machine learning techniques for our problem in numerical computation. And this is for the last point. I would like to say that we don't have to, we have to save our data because we can make use of this data after. But perhaps we don't know for the moment, but it's very important. This topic, it's in this general topic is the topic also that we have organized a mini symposium with Tetsuya Sakurai, Professor Sakurai of University of Tsukuba for parallel processing, Scion parallel processing next March. Thank you very much.
Thank you very much. So any questions?
Thank you.
Okay, so next speaker is Feasibility and the title of it is Challenges for Iterative Method for Sparse.
Thank you, Kengo, and thank you to invite me to give for the third time, if I understand, the talk in this seminar. So today I will speak about some challenges for iterative method and extreme scale for very sparse matrices. So each word is important. So after an introduction, I will focus on sequence of sparse matrix vector product, and I will focus on Fugaku supercomputer. Naid already explained during her talk how it's important to be able to have very fast sparse matrix vector product as what she present, the example one of the examples she present, this part was about, don't remember, but about 90% of the global time or something. After I will focus as an example using this kind of sequence of sparse matrix vector about the very famous PageRank method on Fugaku, and I will conclude. So first, before I would like to say a few words about the evolution of supercomputing and in general how we can mix computational science, big data, and machine learning. Can go already discuss about that. So it's an important project these days. So we speak since many years about convergence between HPC, big data, and convolutional computational computing toward machine learning, AI. So all this is really different world for the moment. So for the computational science, now we begin to solve the end of the Moore law, which has a very important impact. We have new processor, we have network on chip. I will come back on that. We have different kind of accelerators. We have a very high hierarchy architecture for the supercomputer. Even now, cloud as fast as a supercomputer. And usually when you work with graph on sparse matrices, computational scientists use one format called compressed sparse row, CSR or LPAC. They use usually C++ to program. They use 64-bit arithmetic. And usually, as we saw with Naid, and I will give you some example, one of the important computing part is for matrix vector multiplication. On big data is very different. We use a different kind of format like the CO. I will come back. They use different language. They use 32-bit or 16 arithmetic, and they are mainly doing a lot of matrix multiplication. And in machine learning, they use so-called tensor, graph, and also very classical libraries. And they also develop new hardware because existing supercomputer was not designed to do machine learning on AI. So they develop new processor like the TPU and other hardware. And also they saw sometime linear algebra as a game. So it's a very famous paper on Nature where they saw matrix multiplication as a game. They put the rule and they find an algorithm with less operation that nobody find before. So these three different worlds, and this world now have to work together. As can go and is very famous now, that we need to have to mix these different world together to be able to propose new method, new application with a very strong social application. So on the other hand, what is exascale computer? People are saying now that we have exascale computers. So of course, for the top 500, so that means LU factorization, dense matrix, we have an exascale computer. But if we saw the faster computers, the third one is a cloud. And there are different, on the top 10, we have different kind of accelerator, and we have Fugaku without accelerator. So it's not so clear what is exactly exascale computer. And Cerebras propose an exascale computer, which is been based on 16 arithmetic. So also China have exascale computer, but they don't give the data. So it's not so easy to understand exactly what is exascale supercomputer, because the number 3 is a cloud. And if we look some more realistic benchmark like the HPCG benchmark, and we saw that Fugaku is still number 1. So since many semester, so Frontier is just number 2, because so that means there's a faster computer in the world to do some iterative method like this method is a supercomputer without any accelerator. The other have accelerator, so it's not so easy to predict the future. Even if on Fugaku for the HPCG is a sparse matrix, but a very regular sparse matrix with diagonal. So today I will try to, and they just have less than they are just 16 petaflops, so very far from exascale. So today I will try to explain, to focus on how we can, if we have a very sparse and very irregular, not diagonal matrix, what we can expect on this computer like Fugaku. And we also saw that we have a strong evolution. So the 500 computer begin to have the impact of the end of the Moore law in 2010, and now we have a new impact here, which is because we have too many cores on processor, and people don't know how to use it efficiently. So we begin to have. So I don't know if we will have an asymptote or not. And so the impact on the sum of the 501 computer arrived a few years ago, but so it's very difficult to predict the evolution of this. So it's more and more important to focus on the convergence of these different worlds, having in mind that also the architecture and all the ecosystem of supercomputing and HPC will change in the next year. So in this context, we can say that we have exascale computer, but with different, very different ecosystem. And we have a comeback of new programming paradigm. For example, Cerebras is based on a pure data parallelism, close to what was the data parallelism on the connection machine. So it's very different of what is the existing programming paradigm. And so this data parallelism is also very useful at the lower level. And we have another new level of programming because we have more and more nodes, and we need to have graph of tasks. And so is why in US and around the world, there are more and more projects to how to propose new scheduling and new middleware to deploy on supercomputer on this machine. And data flow programming is coming back also with Samba Nova supercomputer. And so we are really at the corner of several new problem on the programming paradigm for the performance and for the convergence between different worlds which have to be able to work together. So is why I will try to take as an example sparse matrix vector computation on Fugaku, because it's really one of the key part of many algorithms where we spend many time on to see how we can, what impact have this new architecture on the very irregular matrices. So we have now a network on chip. That means that now, even on a processor, all the core don't share a unique shared memory. So that means we have a network on chip. That means some data, if some core here have to access to data which are there, they have to go through the network on chip. So of course, the time to exchange data here will be longer than if we are just on one set here called CMG. So we have 4 CMG here. So it's Fugaku is like this. On the Sunway supercomputer in China, don't have so many details, but have 6 of this set of processor. So today I will give you some example where, for example, I use one MPI process in one processor, and with one OpenMP. And sometime I will have one MPI per CMG, and so that means I will have 4 OpenMP process. So because we did the test with both MPI and OpenMP programming. And also something on Fugaku interesting, they propose 2 different kind of topology for the network. You have the network is a 6D hypercube. So you have the classical communication and the 6D hypercube, but we also propose a topology called torus, which optimizes the communication if you have if you use a two-dimensional grid to map your data. So we evaluate the 2 different topology to be able to conclude if a torus connection is better. So just to explain that in any way, if we do are from computational science, data science, and AI, at the end of the day, we speak about sparse matrices, done matrices, transform matrices, or graph. So at the end, we have to do linear algebra. And if we do it, as usually, the matrix is sparse. Usually, if we use a dense method, we have a filling. So we use iterative method, and usually we have sparse matrix vector multiplication. So just to come back, I guess many of you know already how we have the classical matrix vector multiplication. So you distribute a set of different rows in one processor. So if the matrix is part, you compress this block. So something important to understand is that you need to have all the vector x. If you want to multiply a times x, you need to have all the vector x on the processor. So remember that because it will be important after. And of course, you multiply AI by x, and you have a small part of the vector of the result. So if you just do matrix vector multiplication, it's finished. But on iterative method, you have sequence of such computations. So that, of course, at the end, if you want to compute again A times B, you need to have the whole vector B on all the different nodes. So that means you have to have all-to-all communication to be able to send each part of each partial result, each result on one node to all the other one. So all-to-all communication is expensive, but you don't have freelance. You are obliged to do that if you do this kind of computation. So it's very classic. So it exists another solution that you just take some block of column like this. So in this case, you just need to have a small part of the vector x. But at the end, on each node, you compute the result will be a vector of size n. And so at the end, you need also to store one vector on each node. So at the end, you need to add all these vectors together. So just to summarize here, we have two classical methods. One, we just store block of rows. And you need, even if the block of rows are sparse, you need to store one vector of size n. And if you use MapReduce is also very well used, especially on the big data and machine learning world, to do sparse matrix vector multiplication. You need to if you distributed like this your sparse data, you need also to store all the elements of the vector on one node. So even if you do MapReduce, the map will multiply the no zero element by the corresponding element of V. So you need to have some of the elements of the matrix on all the elements of V. And so after you have the sort on the shuffle part, and you have the reduce. But you need first to store all the elements. So if you use MapReduce and if you use the 2D method I explained, you need to store all the vector. So if you store all the vector, what does that mean? If you suppose that the size of your matrix is very, very large, that your number of of node is very, very large, and your matrix is very, very sparse, it's not possible to store one vector. So that means you can store a large number of compressed rows, compressed element, a few rows, but you are not able to store the vector. That means that all the programs which are developed these days are not well adapted, even MapReduce, because we are not able to store a part of the sparse matrix plus all the elements of one vector. So we have to find some solution. And after, you need to have some metrics to be able to test the performance. So we develop what we call the Q-perturbation matrix. We start from a C-diagonal matrix, and with a probability, we move one element of the diagonal to a random position. So if Q equals 0 is a C-diagonal around the main diagonal. If Q is larger, if Q, for example, is equal 1, it's completely irregular matrix. So depending of Q, you can see, you can have directly in parallel compute a large set of matrices with more and more irregular pattern. So just some results we already, perhaps some of you already knows that we collaboration with a Japanese colleague in Kobe. So we evaluate the different formats. So we saw that, of course, CSR and LPAC are the better format for this kind of thing. And here you have the CSR version with the probability Q. When Q equals 0, so it's diagonal. If Q is larger, it's not diagonal. So you see really when the matrix begins to be regular, the performance are quite not so good. So it was expected. That means that when the matrix is very, very irregular, the performance can be not so good. But so it's because all the irregularity generate very irregular communication between the cores. So here it's some result with a matrix, very classical small matrix used in linear algebra to benchmark method. So here, if we use the matrix with the different probability, so here is with one processor, with two processors, with a different format, and we saw here the best. So of course, here is when the performance is where you are in one CMG, one OpenMP per CMG, or otherwise you have 4 OpenMP. And you saw that for this performance, it change a lot. But the best, if you use the best are, of course, using a CSR on the LPAC, and the performance are the best when you focus on CMG. So here it's just for matrix vector multiplication. So if you have a sequence of 2 matrix vector multiplication like this, it's strange, but we saw that the best performance are where you use one OpenMP for all the processor. But I remember that this matrix is very small and a very classical matrix. Now, if we do the same performance, but with the same thing, but with a larger matrix, a very larger matrix, we can, here is in gigaflop, you saw that for this very large matrix with 100 no zero element per row, we saw that the best performance are really where you have one OpenMP per CMG. That means you take the CMG as the most important part for OpenMP, for your programming. And here is the value of Q. So you saw that when the matrix Q when it's C diagonal, the result is still when you have one OpenMP per processor. But when the matrix begins to be irregular, it's better to have 4 OpenMP. So the conclusion is really when your matrix is irregular, the impact of the network on chip is too important because the communication are more irregular on the processor. And so you need to really program with the CMG as the basic element for your programming. So it was the case before, it was when we were still able to store one vector. Now, if we are not able to store all the elements of one vector, you need to use another algorithm. So you need to cut your matrix like this. So if it's sparse, you take some sparse block, because like this, you just have to store a part of the vector. Okay, but of course, it's more complicated. It's a mix of the two other methods. So you have another step to be able to synchronize and to send the communication. So it's very classic. I don't enter too much in details, but in this case, we are able to have we just have to store a part of the vector. So it's okay. You just have to if you have you can. If you have enough processor, you can distribute the vector. Of course, it's very classical and way to do that. And after, if you have a sequence of matrix vector multiplication, that means that you need to redeploy the result because you need to have the element compute here at the end of this method. You have the first block of the vector here, the second block, but you need to have the first block along all these columns, the second there. So you need to have communication to redeploy the data along another dimension. So in this case, you have two methods. I'm not entering in details, but you have two possible classical algorithms. One is to allow you to optimize communication, and the other allow you to optimize the memory, local memory. So we evaluate on Fugaku these two versions. So here you saw that you have and also we evaluate different topology of the network. So here you have, when I say it is 1 MPI optimization memory torus, that means that we use 1 MPI per processor. It's the algorithm to optimize the memory, and we use the torus topology of the network, of the Fugaku network. When we have in green, for example, 4 MPI optimization communication torus, that means that you use 1 MPI per CMG. We take the algorithms to optimize the communication. So here, it's just for one matrix vector multiplication. So we saw that in this case, the classic network is still the best. Here is the time. So here is, but it's just the matrix vector multiplication. We don't have to redeploy the data. In this case, we have one matrix vector multiplication plus the redistribution of the data. So it changed, is now torus, which is better. And after, so is a way, here is a weak scaling. We add the number of zero element per node is a weak scaling. And after here, if I have a sequence, so I have the matrix vector multiplication, the redistribution of the data on the matrix vector product. So we saw that in this example, the base is to have 1 MPI process, I mean 4 MPI, 1 OpenMP per CMG plus MPI, and to have torus topology for the network. So here it's the same, but with more non-zero element per node. And we still, so here it's still ongoing work. So we still have a memory problem there to solve, but we have the same kind of conclusion. So about the PageRank rapidly. So PageRank, we experiment PageRank for many applications, especially in graph convolutional network. When you have draw page technique, we first rank the node or the edge to be drawed. And so in this case, we have for graph convolutional network, or even for the transformer method, we have a lot of sparse matrix multiplication by skinny dense reticular matrix. And so it's already published result when we have when we are able to store all the element of the processor. So rapidly, the computation we have to do is mainly based on matrix vector multiplication for the page rank plus a few vector computation. So it's really like for the Krylov method now at present is really on the matrix vector multiplication that we spend many time. So we experiment with the same after. We experiment on Fugaku with the classical networks topology with one MPI per node, so is node or CMG, that means one open MP by CMG. And we saw that for page rank, when we are able to store all the element of one vector per processor, is really better with the CMG. Performance are always better, and of course is always better with CSR on LPAC that with COO on the other version. So now, so I will join that. So it's the same. Now the result when we are not able to store all the vectors. So we distributed the vector. We have on each processor, we have a set of sparse compressed row plus a small part of the vector, not all the element of the vector because it's too large. So it's a more ongoing, still ongoing work. So we saw that, so is a weak scalability. We saw that the best is when we have the torus, we use the torus and we use the algorithm to optimize the communication. But when you saw, it's strange because the weak scalability is very nice for this one. Here at the beginning, but we have to test with more nodes to see how it works if we add the number of processors. So as a conclusion, first of all, I wanted to present you some results for the conjugate gradient. So it's finished, but we still we have to do some analysis because, as you know, for the to evaluate the conjugate gradient, we need to have a symmetrical definite positive matrix, and to have a sparse matrix, irregular, definite positive, and symmetric. We succeed, but so we still have to analyze. But so anyway, all this result with the conjugate gradient will be present on the mini symposium we organize with Kengo Nakajima and Makiru in PP 24 soon. So as a conclusion, so it's very important to understand that sequence of very large, irregular, or dynamic, because if you do machine learning like graph convolutional network transformer, the structure of the sparse matrix is dynamic change. So it's non-Hermitian, is irregular completely because it's a graph, and is dynamic because the number of the element we drop on the element, random element we change during the computation. And the matrix by vector and by rectangular skinny dense matrix on a very large supercomputer, that means with a large number of cores, it's not so easy because we are not able to store all the elements of one vector. And we have to do that because it's very important. And as is this kind of very easy mathematical computation, the matrix vector multiplication, is really the key for many applications in machine learning, computational science, and big data. And we need really to be able to optimize that and to understand that a lot. And of course, we can also use mixed arithmetic. We can to store the data. There are many things to work. So it's really a very interesting period these days because with this convergence between different scientific domains with new architecture, I think is a very challenging time. But there are a lot of very interesting research topics to work on, and I hope that we will be able to do part of that on the very long French and Japanese collaboration we launched 20 years ago. Thank you for your attention.
Okay, so next speaker is from online. Speaker is Dr. Masatoshi Kawai from Nagoya University. He's my former colleague.
Okay, thank you very much for introduction. So can you hear me, my voice?
Yes.
Okay, thank you very much. Okay, so today I'd like to talk about this title. So it's a development of applications in applied or adaptive precisions. That trying to make sure that, okay, so that this outlines. The objective of the using the adaptive precision is improving performance of the applications. So in this talk, so our target application is sparse matrix vector multiplications or the ICCG method. But on these applications, so these are the memory bound applications. So by using the low or the adaptive precision, so we can expect a performance improvement because of reducing the memory accesses. The next is about the low adaptive precisions. So this is the example of the adaptive precisions. So FP64, 13 and 16 is these are the standardized by the Iterative 754, and this data format is widely used. The adaptive precision is this like this. So for example, FP42, so the fractional part is reduced to 32-bit compared with the FP64, and the FP21, so that it is also reduced from the 23 bits to the 12 bits. So by this reducing, so we can expect a performance improvement. But that is important part under notification. So there's no FPU that supports adaptive precision. So we need typecasting in the operations and the load over the source. So we are introducing the concept of the memory accessors. So it means that these are the this part of the computation. So this memory accessor is called before the computation and after the computation to store like this. So there's some variations of the memory accessors based on the some kind of implementations. So in this talk, we introduced two patterns of the memory accessors. So this is one of the memory accessors. So we call the array of structure type, and sometimes so we can call as a packed types. So this is examples of the FP42 data format. On the array of structure type, so we pick up the 3 elements of the FP42 like this and packed to the 128 bits like this. So by this change, so we can call it as a packed data types. So this is our work, and we also propose the FP21 to FP42, and like this. And the other one is the structure of array data type. So this is a example of the structure of the array size format, and this is a 42-bit data format. Then so we separate the 48 data byte data to two parts. So one is a 32 bits and the other is a 16 bits. And this part is making us the other arrays. So for array of the precision value and the array of each word is allocated separately like this. And to obtain an element from the array, the element are taken from the two separate arrays and concatenate them into the values. So this is another approach, and this is proposed by Daichi Mukunoki and Mamura. And this research is published last month at the MCSOC 2023, and this paper is nominated for the best papers. Okay, so the next slide shows the expressive ability of each data format. And on these tables, the green shows the structure of array data format, and the blue shows the array of structure data formats. So then this part line shows the format of the each state format. So the S is the significant part, and E the exponential part, and M is the matrix or the fractional part. And the decimal digits is this line shows the decimal digits of each data format. So basically, so the higher data format has a better more decimal digits, and also the max exponential part. The data size is different between the AOS and SOA. So when we use SOA, so the target adaptive precision is separated to the some arrays like this. For example, the 56 bits is separated to the 32, 16, and 8 bits arrays like this. The comparison between the AOS and SOA. So the versatility of the SOA is better than the AOS. So it's been the SOA is more suitable for the many type of adaptive precisions. So of course, the AOS is able to apply some type of adaptive precision to SOA, so like FP42. But we try to apply the FP42, FP14 with the algorithm structure. So there's a 24 zero paddings. So 72 bit zero paddings are required. So there's this is not good for performance improvement. But by appearing the FP40 with a structure of array, so there is no padding. So this is a good point of the structure of array types. And also the AOS require the code modification. It is because the 3 elements are handled as a 1 element for the load on the stores. But SOA is not needed for any code modification. So this is also a good point of the SOAs. Good point of the AOS is catch hit ratio is the catch hit ratio of the AOS is better than the structure of array data types. It is because the SOA increases the number of strings. For example, the 56 bits, so it requires the 32 arrays and the 16 arrays and 8-bit arrays, the separate arrays. It's meaning the number of streaming lines is increased. So in this case, so there is 3. It requires the 3 streaming lines. So the result of the catch hit ratio is of the AOS is better than the SOAs. Okay, so the next slide, so I will show about the storage format. It means so if we improve the performance of the applications by using the adaptive precision, so that each application must be limited to the memory bandwidth. So it means in other so each application has completely use the memory bandwidth. So the chances are very well-known approaches, but it is difficult to improve memory bandwidth, memory accesses. So we use a Celsius sigma format. The ELL is already introduced the previous talk, so we need to show the Celsius sigma format. So on the Celsius sigma format, so we separate the target matrix to based on the sorted scope like this, and sorting the number of number of elements in each row like this. After that, so we apply the chunk size and the blocking like this, and this remaining part is adding some zero paddings like this. And the computation of the order computation is like this. So on this order, so we can expect the simulations. The computer is the ELL, so there's the number of zero padding is reduced. So this is a good point of the Celsius sigma format. So and on the numerical evaluation of the AOS types data type, so we use the Celsius sigma format. And the next slide shows the adaptive multi-level blockings. So this is we can introduce as the Celsius sigma with index compressions. And on the previous slide, so on the Celsius sigma format, so the row is sorted with the number of elements on each row, but on the IMB approach, so the target application is separated to not only the rows but also the columns like this, and apply the Celsius sigma format like this. And after that, so moving this element to the others outside and moving the zero padding part like this. So by this approach is the indices is completely make same indices like this. So by this approach, so we can compress the indices part. And on the numerical evaluations of the ASE format, so we use AMD format like this. Okay, so the next slide shows the numerical evaluations of the each data format. The initially, so I like to show the numerical evaluations of the array of structure data format. On the numerical evaluation of the array of structure type. So we use three systems. So one is the Sparse, and the second one is the OpenCX. So this is already retired. The last one is the Feasibility Odyssey. Sorry, now 1 and 2 is already retired. So the last one is service. For the condition, the applications for applying the array of structure data, so we pick up P3D applications. And the degree of freedom of the target application is about 70 million. And some difficulty on this evaluation, so we try to change the thermal diffusibility of this part. Then they make the changing the conditions of the target application. Target programs. And for the adaptive precision is applied to the ICCG solvers, or whole ICCG solvers. This is a condition of the ICCG solver part. And for the numerical evaluation, so we combine some data types like this. So there's some combination. It means some data combinations of the data format. So for example, the FP42, FP64, meaning matrix is stored with FP42, and the vector is stored to the FP64. And on the OpenCX and OpenSparse, so we only apply the adaptive precision. So on the issue of the compiler, so the adaptive precision is not applied to the Wisteria Odysseys. And before show the performance evaluation of the adaptive precision, I would like to check the performance of the P3D applications with the Celsius Sigma format. So by using a Celsius Sigma format on the P3D application, so the performance is drastically improved. For example, on the Wisteria Odyssey, so Celsius Sigma format, performance of Celsius Sigma format is 3.3 times and 1.9 times like this. And on the numerical, the user memory boundwise is measured by 112 gigabits. It is measured by the physical profile. The memory boundwise of the streaming triad benchmark is 840 gigabytes per second. So this is very close to the this streaming result. So this is very good result. And based on this results, the OpenCX and OpenSparse is calculated like this. These are also very good results. So the application is very well tuned for each application, so we can ready to performance improvement by using the adaptive precisions. And the next slide shows the result of the applying low order adaptive precision to the ICCG method. The left graph shows the number of iterations, and the right graph shows the relative errors of the result of the result of the computations. On the left graph shows the x shows the lambda, it meaning condition of the target problems. And the y-axis shows the number of iterations. So if the target condition of the target problem becomes a condition, so the number of iterations is increased like this, and the lower precision, so there's more iterations like this. But we can check the rate errors of the each result. So FP21 is only acceptable on the the best conditions. After that, so the database make worse. So it is really difficult to use their applications. And compared with this result, FP32 is not so bad, but if more than 100 values, so make the data make larger, and this is very difficult to use this part as earlier applications. On the result of FP2, completely same to the FP64, so there's no lines on these graphs. Okay, and the next slide shows the result of the computational times. With like this, so the X shows the problem conditions and the Y shows the computational times. So by using the low order adaptive precision, so we can get a performance improvement like this. So actually, so by using FP21 and FP30, so it means the 30 or 40% faster than the FP64, the FP64, and the FP42 is also more than 10% performance improvement compared to the FP64. So this is the result of the ALM structure type data format. And the next slide shows the result of the structure validated type. So on this numerical evaluation, so we use 4 systems. So MDPX and the Interzeons and the AR100 and the MI100. So these are the compared options like this. And for the numerical evaluation, so we use sparse matrix vector multiplications, and the target application is downloaded from the Florida sparse matrix collections like this. And so this is the order with a number of non-zero elements. So this is this order with this part. And so the next slide shows the result of the performance of the sparse matrix vector multiplications. So the upper graph shows the gap flops per second, and the lower graph shows the relative execution time to the FP64. The result is very interesting, and the tendencies changes to each data matrices. So, but we can expect this tendency with the size of matrices. So the largest part is so this matrix is the most smallest matrix. So this is completed on cache computations. Sorry, just a please. Sorry. I'm sorry. The 0 is the largest matrix, and on this part, so the computation is a completed memory bandwidth tendencies, and the performance is proportional to the bit length. It means if you use a lower or the adaptive precision, so we can get performance improvement like this. This part is larger data format is out of cache, but smaller, shorter bit computation with a smaller bit is on cache computations. As a result, so the performance improvement or the lower precision is shows a large performance improvement like this. The last part is on cache computation. So the AMD has EPIC has a large caches. As a result, so this result is completed on cache computations. As a result, so it's difficult to get performance improvement using the lower and adaptive precisions like this. It is because the overhead is apparent. So because of increasing the streaming lines like this. So this is the result of the EPIC system. So out of cache and the intermediate part and on cache part, so the tendency is changed like this. And the following result is similar, very similar. So this is a result on the Xeon system. So here is the out of cache part, and this is the intermediate part. There is no on cache computation part. So out of cache part, so same to the AMD, this EPIC result. So this precision shows a better performance improvement like this. And the intermediate part, so the performance is made larger like this. And so the next show the result show the A100 result. So the A100 result, so the all computation is out of cache. So as a result, so we can get performance improvement by using the low precisions like this. So and this is the result on the MI100. So this is also same to the A100. So but by using the reduced precision, so we can get performance improvement like this. Okay, so the conclusion. So by using so in this talk, so I introduced the AOS and SI type the adaptive precisions and evaluating the each types with a different system and applications. And so future, so I'm sorry, so there's no comparison between the AOS and SOA, and we are very interested in the performance of the comparison of the AOS and SOA. So I just the comparison between this format, and in the next I like to try the hybrid approach with the AOS and SOA. So for example, the matrix is stored with the AOS and the vector is stored with the SOAs, like this. And also we need the auto tuning so to find the best combination of the adaptive precision for each applications. And the next slide, so we try to adding the numerical verifications. Okay, so thank you very much for your thank you very much.
Thank you. So any questions, comments? So do you have any idea of the so could you go back to the last page?
Sorry.
About the so why the AOS is good for ICCG and the SOA is good for SPMB?
So basically, so the SOA is suitable for example, stride access like vectors for on the matrix multiplication. So I guess so SOA is suitable for the vectors and the matrix for the stored matrix. So AOS is better because on the matrix, so there's a continuous accesses. So this is one of the my recommends of the stores. And also I will apply the ICCGs to with these approaches in the future ones.
Okay, any other questions? Okay, thank you very much.
Thank you very much.
This is the end of the first part, and then we are a lot behind the schedule. Okay, let's take a 10-minute break, and then we start the next part from 5:10. Let's start the second part, and then we have two talks from the Fugaku-Next feasibility study supported by Japanese government. And the first talk is our colleague, Professor Shimokabe, and so he will talk about the overview of the system research by the RIKEN team and activities of its application group in feasibility studies.
Thank you very much. I'm Takashi Shimokabe from the University of Tokyo. So in this presentation, I will provide an overview of the system research by the RIKEN team and introduce the activity of the application group with some of the effort of the application subgroups. So here is sorry that is very crowded slide. This is a project overview, official project overview. This research activity by RIKEN. and for the Fugaku-Next in the 2030. This project aims to realize the versatile computing infrastructure that can execute the entire workflow by making the full use of a wide range of the computational methods, simulation technique, and big data scale. So that we conduct investigate on the architecture, system software, and library technology, and through co-design with applications. So we have the three research groups. One is about the architecture. They are investigating the technology, the possibilities, and the performance of the entire system or its the component. And in the system and software and the library group, they drawing the roadmap for future system software development in Japan. And the application group, building the broad benchmark set to evaluate the multiple architecture choices. So we have been working on this feasibility study for 2 years, and will continue for 1 more year. So this is the organization of the system research by the RIKEN, the big team. And you can see that from this, many research institutes and the university in Japan are participating, and also it's small, but here is the famous chip vendors such as the Intel, AMD, and NVIDIA, also participating in this research. And here is the key research item for the node architecture selection. So as you all know, we need power efficient compute node, and then investigate the use of the accelerators. So there are the CPUs and the GPUs and the matrices, the accelerators. So each with the different characteristics. And it is necessary to find this is sorry, I read the chat. That's something difficult to hear about. So the different, and it is necessary to find the optimal balance and integrate them. So, and also the programming productivity is also important. So the interview with the application developers and the quantitative benchmarking analysis are required. Sorry. And here is the performance projection in the power constrained scenarios, and I will. And the lower the right figure shows the performance on the horizontal axis and the consumption on the vertical axis. So the power consumption is constraint in the building system. So the under 30 megawatt power budget. So from the 2 to 4 exaflops can be achieved by using the GPUs, and from the 20 to 100 exaflops can be reached by the matrix processors. So it is necessary to decide how much power to dedicate to the which processor group. So here is the summary of the system performance projection. Here is the processors and the memory. That is the performance and also the memory bandwidth. So under the consideration by the architecture group, as shown in the previous slide, so with the application research group is conducting the research on the computational resources required to realize the leading edge research result with the Fugaku-Next. So we consist of the 12 subgroups, which comprises the application fields of the computational science, the social science, and the data science. So we investigate the wide variety of the application using the general indexes such as the total computation, the arithmetic performance, memory usage, and the internal total communication performance. So in addition to general indexes, this research includes the survey of the various indications that define the characteristic of the application program, such as vital flops, SIMD, instruction utilization rate, and the productivity. So in parallel with the investigation of the individual applications, so we are investigating the communication avoidance and the communication reduction type algorithms and the state of the art the algorithm in the machine learning from the common perspective for the applications. And we will investigate the necessity and characteristics of these algorithms in the application running on the next generation computer platform. So in order to conduct these studies, so we have adapted the organization shown in this slide. So the entire application research group is divided into the 12 subgroups, and 8 of these subgroups are classified as the pure application groups, where the subgroups belong to the various scientific fields such as the life science, the fundamental science, and the weather and the climate, and so on. And on the other hand, the 4 subgroups are called the computer science group, to which belong subgroups that work on the algorithms and the benchmark building and the performance model building. So the 6th group does research on the common algorithm in the various scientific fields. And here is some example of the roadmap of the target science in the Fugaku-Next era. So the first one is the target science in the life science area. So the one is they will assume that they build a cell digital twin by using the simulation and the AI and the experiment. So currently they take about 8,000 days with 60,000 nodes in the Fuga for the 10 microsecond simulation. But in the 2030, they assume that they reduce this time and from about 3 months by 100 performance improvement. And also the other example is about the social science area. So they perform the traffic simulation of they try to perform the traffic simulation of the entire Japan in the 2030. So currently now they are just only for the simulation on the Kinki region that is around the Osaka. So, but they will extend this simulation to all over the Japan in the Fugaku-Next era. So and also the simulated for the full Japan, and including the prediction of the disaster impact propagation with the economical mutual interactions. So the third example is in the weather and climate science. They are currently they currently analyze the Japan area for the 10-hour ahead of time with 2-kilometer horizontal resolution. But in the 2030, they can analyze 80 hours ahead of time with 200-meter horizontal resolution. So actually about the related to this area, so the Japan Meteorological Agency also participating in this application group. So the research and the result obtained from this feasibility study will be used to improve the accuracy of the weather forecast in Japan. And also, the next talk about the benchmarking. So the benchmarking, of course, is necessary for the quantitative evaluation of the architecture. So we built the benchmark and or micro benchmark that reflect the characteristics of the representative application. The developed benchmark were already provided to the architecture research group and the system software and the library research group, and to contribute to the promotion of these research studies. So based on the feedback from the architecture research group and the survey result of new algorithms, the subgroup in the application field reviewed the target program on the next generation computer infrastructure and reflected them in the science roadmap for each field. And through the above survey and research activities, so we will classify the role that the Fugaku-Next should play. So here is the list of the benchmark calculation. Currently, so we selected the H benchmark for this the evaluation. So the other benchmark, we use other benchmark application. So we use the traditional HPC applications such as the weather and climate and or manufacturing or something like that, and as well as the AI applications, including the LLM. So the weather forecast model that is not the normal one. That is for the more real one. So that means that we use that application with including the data simulation, and it is one of the workflow aware the benchmark. And also by surveying the application developers, so we promote the smooth collaboration between the system software and library groups and application research groups. So here is some examples of the survey results. So the one of that is the programming language. So this is the graph, and this graph said that the four are most commonly used in Japan, and followed by the Python, C, and C++. And only one respondent used only Python. So that means that the Python support remains important. And about the development for the accelerators, so more than half of the respondents had no or little programming experience with the accelerators. So most of those with experience developed for the GPUs using OpenACC or the OpenMP. then almost all of the developer with no development experience indicated that the directive-based programming support would be the desirable when the accelerator deployed. And also the another survey result is about the performance portable programming. So only a few respondents have used it, just one. In this case, but many would like to use it in the future, depending on the developing the course. And so when porting to the accelerated tasks, the porting and tuning with the SIG, the HIP, and the C++, the compatible programming framework is also the option in the C case, and also the standard parallelization is another option for the porter. Maybe the open ACC is another choice. And also the next Fugaku-Next era. So the many science applications are expected to utilize the AI. So therefore, there is a need for the AI for science workflow, the benchmark. So in the digital twin and the society 5.0 subgroup is investigating the flowing application. So we developed the data-driven parameterization model for the weather simulation by integrating the simulation and the machine learning. And by replacing the part of the simulation with this model, we can increase the resolution and the performance of the simulation to achieve the global weather simulation for long period. So actually, this application is shown in the Professor Nakajima's slide. In order to integrate the simulation and the data and running fun in such application in the previous slide, so we now operate with the VLX01. So the Nakajima sensei already explained this system, so that I will skip the detail about that. But we are developed the benchmark for using this system, and the benchmark that is also shown in the Nakajima sensei's slide, and that is the atmosphere ML coupling the one. So we built this benchmark code. We make this kind of benchmark code. So this simulation includes two parts. So the one is the high resolution model for the detailed simulation. Another is the coarser model for the parallelization. So we replace this coarse model for the parameterization with AI, and this part requires 25% of the total computation. In this machine learning process, the air density, the internal energy, and the density of the water vapor are the input, and the gradient in the time direction is output. And the PyTorch is used as a framework for the machine learning on the aquarius, and multi-layer perception with 3 layers was applied in this. And here is the input, the left side hand side is input, and the middle is output by the simulation, and the right hand side is the output by the inference. So by using the library that can communicate between the different type of system, in the heterogeneous system. So we are building the benchmark that allow us to investigate the communication performance in the various communication patterns. So this one, the NICAM, that is atmospheric the model run on the Odyssey, and the machine learning part run on the Aquarius. And but another option is also can be selected. So another benchmark for the digital twin is local wind simulation with mesoscale meteorological data assimilation. So utilizing the AI technology is essential for the consideration of the next computer system and the computational science roadmap. So also the research on the surrogate model for the large-scale simulation and the generative AI is already underway in Japan. But this activity have not been reflected in the HPC, the computational science roadmap. So we decided to writing the roadmap for AI for science. With the relevant the HPC and AI expert and researchers. So eventually this AI for science roadmap is integrated with the HPC and the computational science roadmap. So using this AI for science roadmap, we will investigate the computational environment needed for the AI for science and improve the benchmarks. And the Japanese version of this AI for science roadmap will be available at the end of this March. And the English version will be published by the end of this year or the early time of the next year, I think. And the next steps in the feasibility study project. So we will continue this study for the one more year, and we will select the architecture system candidate for the more detail and for the next generation system. And that is part of the architecture group by the architecture group and the system software and the library group. And the application side, we are here. So we are now building the benchmark for the fair the architecture comparison, and also we should considering the workflow benchmark that integrates the computational science and machine learning. And also we will collaborate the operation technique and the new computing paradigms teams, and so such as and also we extend the computable area by the HPC or the quantum hybrid platforms. And this is my final slide, the summary of the talk. And we are conducting the system research, the RIKEN team for the PD study on the next generation supercomputer infrastructure. So there are 3 teams, and I'm the one of this application research group. And today I introduced our activity and also the related to the benchmark and AI for science. And thank you very much.
Thank you very much.
Thank you very much.
Next talk is also my colleague, Professor Hanawa. So he's leading another group for the feasibility study for operation technology.
Okay. Thank you for introduction. I'm Toshihiro Hanawa, and I would like to talk about our activities, the operating technology research and the feasibility study. Yeah, so this is official, not official summary slide, and so as Shimokabe-san mentioned, so in the feasibility study, we have so 4 research survey team, and so 2 teams so for the regarding the system development, and so 1 research survey team is so novel computation principles, including the quantum computing, led by Professor Amano, and so I covered so our team covered so everything so excepting these topics, so including so some usability, and also the next flagship facility, and so power and carbon neutrality, and so on. Okay, so our team is so operating technology survey research team from the very wide range of so collaborators, so including the supercomputer resource providers, including the RIKEN RCCS, so they provide operate the Fugaku system, and also the HPCI shared storage, so with a large capacity, so the 50 petabytes, and also the ASE, and also Tokyo Tech, AIST, Nagoya University, Osaka University, and Kyushu University. And so from the second year, we involved some commercial cloud vendors like Microsoft and Oracle. So in our team, to realize sustainable next generation computing infrastructure, not only the flagship system, but also the HPCI, our national universities, supercomputer centers, and also the commercial cloud or and so on. So we conduct studies by aggregating the knowledge obtained by the design and operation of the various systems. Because we our colleagues come from the operation side. So we would like to form the next HPCI systems. So to gather this knowledge, and so the final goal is also aiming to provide platform to contribute to the promotion of the Society 5.0 and the achievement of SDGs, and to provide a common infrastructure that supports research DX for all domestic researchers. And so in our team, we usually discuss in the following 3 layers. So first is very low level, including the facilities and the infrastructure aspect, and also including the carbon neutrality. And so second layer is some kind of a system software layer, including resource management, and some workflow for the Society 5.0 workload, and data utilization. And so the final layer is highest, some kind of a very abstraction layer, operation policy and the user perspective, such as next generation HPCI. Okay, so this is overview of the HPCI. HPCI stands for the high performance computing infrastructure in Japan. And so the HPCI provides a single system view. But actually that's not sufficient. So that we would like to improve such kind of utility. And so in the HPCI, so several supercomputer centers are connected by the SciNet. So NII, National Information Institute of Informatics, operates these academic networks, so named the SciNet 6. And so these supercomputer centers are connected by this network. And also that we provide two very big shared storage. So actually, these storage are automatically duplicated, so very secure storage. Okay, so in our feasibility study, we investigated the future computing resource capacities. So from by 9 national universities, supercomputer centers. So so this is so this graph is come from the list. So some front office of the HPCI. So this is this graph shows request and allocated resources for HPCI. And left hand side shows for the Fugaku system. And so brown is allocatable for the Fugaku, and yellow part is requested by the proposal from the users, and the gray part is actually allocated on the Fugaku. So the resources, latest one is still there and examined, but so in last year, totally the allocated resources, almost 300 petaflops resources are allocated for the requested project. In contrast, second tier, total number of the second tier resources are quite small compared with the Fugaku system. So in this year, allocatable resources almost 50 petaflops, and requested is not so small part compared with the Fugaku. So this gap is also quite big. So there is more than over the 5 times difference in the amount of the resources that can be provided between the Fugaku and the other second tier computing resources. So in this observation, total of the second tier system will never surpass Fugaku resource. And actually, this is future operation plan on the second tier systems. So we surveyed the planned system installation by supercomputer centers, and as you can see, until 2027, the number is relatively accurate, but after that 2028, not so accurate that number, and totally the total amount of the second tier catch up just for the Fugaku at the 2028 time frame. And this is number of the peak performance. And actually in the HPCI second class provider, approximately the 30% of the peak performance. So quite small compared with the Fugaku resources. So this is a very we are worrying about this condition. And we should consider about to fill these gaps in near future. Okay, and this is also for the next or beyond flagship system development. So in the K-computer era, so K-computer lifetime was almost 10 years. That was too long. But so the current Fugaku schedule, so there is no schedule for the retirement. So actually, so it is not decided yet. So the problem is transitional period to new system after this retirement. But so the biggest issue is so there are no current plan. And so to fill the gap, as I mentioned previous slide, so the ideal plan is we introduced two system, and so integrated the concurrent operation can be saved such kind of a gap. And so yeah, of course, so first shot is first time is slightly difficult to catch up this kind of manner, but ideally, if we can install the two systems and overlap the several years, so that we overcome such kind of difficulties. Okay, so if possible, so this form can save the ideal operation. So the lifetime of the computer system is typically at most 6 years, and so we can replace after the 6 years. But in that time frame, another system available, so the user can survive such kind of difficulty. Okay, so so actually, we need to discuss about facilities, so that how to install the next system. So actually, the current computer building in the Fugaku is insufficient in terms of additional installation space and the power facility and capacity to install Fugaku and the new system in parallel. And so the biggest issue is major renewal is required. So some very big, huge systems, so cogeneration system equipment is end of life, so that we need to replace. And also the cooling pipe already worked, so that we need to replacement. But it will take around 2 years after the shutdown of the Fugaku. So we investigated such things, so that we need to discuss this kind of expansion and enhancement of the facility. But not only the system architecture, but also these kind of facilities. And we investigate toward the carbon emissions reduction of the supercomputer systems. So this is a Japanese government official announcement. So the government says emission by the 46%. So in the 2030, and carbon neutrality will be achieved in the 2050. So this is quite difficult target, but we have to try to catch up this kind of reduction. So in FS, we discussed this kind of a scenario. So how do we make Fugaku's current facilities to the carbon neutral compliant? So there are many power and cooling facilities in the Fugaku data center. And so that we consider the feasibility for the how to obtain the renewable energy or the renewable fuels like hydrogen, and also the how to efficiently use the power using the batteries, and also the how to reuse waste heat in near the data center. So actually, there are several difficulties. And so we should investigate some kind of a quantitative studies, so that we need to keep this discussion in over the next years. Okay, and so the most important, most biggest reduction come from the cooling system. So the current Fugaku is just only chiller use, and so because the Fugaku system requires very low temperature of cooling water. So in next system, we consider about much higher temperature of the hot cooling water. So in our investigation, the 32-degree temperature is so good for the power efficiency. So in that case, we just only need a cooling tower, and PUE might be lower than the 1.1, and so the 20% better power efficiency compared to the chiller system. Okay, so currently we have several infrastructure and facilities to investigate such kind of efficiency. So our Forest Parks 2 system and also the Tsubame 4.0 in Tokyo Tech has several accurate power measurement systems can be expected. And so during the operation, we can measure such kind of power consumption with accurate power consumption, and also we will measure the power consumption of the water cooling system and the air cooled system. Okay, so from here, another topics I will mention. So the HPCI has a single sign-on mechanism, but current mechanism is quite old, and also almost no longer supported to the global toolkit. So we moved to the new international standard authentication system named the OAuth 2.0 and the OpenID Connect. And so if we can use this protocol, so some kind of very useful the Gakunin Federation system. So if this authentication system can be utilized, so that every supercomputer system does not need their own authentication system for the HPCI. So instead of that, we already have a Gakunin ID. So in this federation, very useful. But the one issue is how to certificate the level of each participating organization, match the security level of the HPC operation. So we need to discuss about such kind of level, security level. And also we need to discuss about security requirement. So currently we operate the HPCI system based on these requirements for the security. But recently some security attack is a very difficult to avoid. So next generation of the security guideline should be the cyber resilience, the ability to minimize damage based on the intrusions and the internal fraud should also be considered. So we would like to determine some kind of security guidelines based on the cyber resilience considerations. And also we should consider about software safety checking mechanism like automatic check like GitHub, and also in the Docker container, so the SBOM is also good point. And so we are considering about usability for next gen HPCI systems. So already available for the web-based research data management platform named Gakunin RDM developed by NII. So this can be utilized as a portal system. And also recently in the Fugaku system, Open on Demand is already available. And also we try to use Jupyter Lab as a front end for the supercomputer system, batch scheduler system. So we would like to promote this kind of web-based user interface for the some kind of novice users for the supercomputer systems. Okay, and in the next generation computing infrastructure, data utilization is very important. But many kind of data exchanges are required. So in that point, we need some kind of academic cloud is important. So the academic cloud with virtual machine, so their flexibility is very good in connecting various kinds of computer resources, edge devices, and storages. So already we promote MDX as an academic cloud in Japan, operated by 11 national organizations. But actually there is no guarantee for the operational cost. We asked to the government some kind of support for such efforts. Okay. And we need in near future the security or privacy conscious storage, and also such kind of trust execution environment will be needed in near future. Okay, and yeah, I would like to skip. Okay, this is a summary. So in the operation technology team, we would like to improve the HPCI operation into the next generation, the post Fugaku era. And the sustainability is most important point. And how to fill the gap after the shut down the Fugaku system. And we would like to change some kind of a good mechanism for the sustainability, for including the flagship, not only flagship system, but also the second tier systems. And also not just only the supercomputer system, but also the academic cloud and the storage are also important. Thank you very much.
Okay, thank you very much. Thank you very much. Thank you very much for long time. I'm sorry. So this is the end of the 46th ASE seminar. So thank you very much for joining, and see you next time.